I have a general question, which is valid for any smooth representation of a reductive periodic group with coefficients in any field of characteristic P or L or 0 or field that is not algebraically closed. As because it's very general, it should be simple to solve it. But we'll see. So what is my general question? So, general question. So I take F, a finite attention of QP, or LP of T. Any local non-Archimedean field of residual characteristic P. And I take G, connected, reductive, and group. So, Caleta, noise here, I didn't dare to use the non-connected reductive group. So, and G is equal to G. This is what I call a reductive periodic group. G. And I choose a field, R. This will be my field. So, no condition of characteristic, no condition of algebraically closed. And I take pi, which is admissible. R representation of G. Admissible, this means that on the space, so I put this R, on a R vector space. This V, so this means that V is equal to the union of this invariant vector by K open compact subgroup. So this means smooth, but it is admissible, meaning that the dimension of R or V not infinity. I want to have a question as simple as possible, so I will suppose it is irreducible. But it is not really necessary, but put it irreducible. And my question is trivial if this vector space is finite dimensional, so I suppose it's infinite dimensional, and most of the representation, it is this condition, infinite dimensional. So the question is the following. If you suppose that H is a Morra group, like a parahoric subgroup, for instance, my group, and HG is a G congruence subgroup of H. So every Morra group appears with a filtration given by the J congruence subgroup goes to 1. So what the representation is a union of the vector invariant by AG for all J. And the question is, can you find a polynomial which depends on pi on H of X with integral coefficient, very important with coefficientism, such that the dimension of V invariant by J is equal to P, become polynomial when J bigger than some integer. Question. And if so, what can you say about the degree? So what is this polynomial? What the degree, the coefficients? What does it mean? So why I am asking this question? Well, because this question was in the mind of many people since 60 years, I would say, for complex representation. We don't know the answer for complex representation. So why now, and I'm just out of the blue asking this question? It's because of Stefano Morra. He's responsible. Well, so yes, 10 years ago, Stefano Morra looked to the irreducible representation of GL₂QP over a finite field of characteristic P. And he started to compute the restriction of this representation to Morra groups, the filtration of Morra group of GL₂QP, and he found the polynomial. Yes, there is a polynomial for an irreducible representation, admissible representation of GL₂QP over a finite field. Okay? There is a polynomial of degree 1 with coefficient integer, so that this happens. So this is, then when you see that, if you have some experience with complex representation, you think, well, maybe this should be true and checked for complex representation. But I show you, I cannot do that for complex representation. But maybe it is true because for GLN, we know it is true for complex representation. So I think I made a mistake. This should be, what? Ah, I can. Good, thank you. Oh no, up. Okay. How do I do that? And then I should go. Okay. True. Well, as for when P is from prompt 2, G is equal to GL₂QP. R is a finite field. Characteristic is equal to P. And the Morra group, you start with the pro-P worry, which is a mole paragon group, or you start also with a 1 plus P and 2 ZP. This is Morra. So it is also true for when you take G, so complex numbers, GL and F, pi is a reducible cuspidal, super cuspidal. This is how in 1970. So last year, I gave many, in 2022, I gave many lectures on this question and a little more, telling that I could prove it for GL and F when the field is in a field of characteristic different from P. And that I was thinking it should be true also if we replace GL and F by GL and D, where D is a dimensional algebra. And when I was writing the proof, an article I discussed with Guy Henniart the fact that it should be also true for GL&D, and we discuss it, and now we have a paper together where what I will tell you is proved. Okay. So my talk, I will start with the complex numbers. The field is complex numbers. And I put another restriction that F over QP contain QP. The characteristic is 0. Then the answer to the question is almost yes. There is a polynomial, but the coefficients are rational numbers. And we don't know how to prove they are integers. What? Because I like better integers. No, the polynomial will take integer values. So you know that the coefficients are rational numbers. Okay, but if the coefficients are integers, much better. But you don't do number theory? Well, because I will prove that when you take a GLN or an inner form of GLN, they are integers. So the question is, do you have a counterexample where they are not integers? So here there is a restriction F contain QP of characteristic 0. So theorem with Henniart, F can be of characteristic P. So when F here, I will explain to you why this is true with rational coefficient. It comes from the Array-Chandra local character expansion. It comes from this, which this is in the 19, and also from the homogeneity of nilpotent orbital integral. So there are many young people who don't know maybe what is Array-Chandra local character expansion, so I will tell you what it is. You have your representation, and you will restrict your representation to an open compact subgroup that is small enough. Small enough so that it will be the image by the exponential map of a lattice of the Lie algebra. And you look at an endomorphism, the space V, which is written usually like that, F of F dg, which is sum over G, the F of G, pi of G, dg. So you choose a Haar measure on G. And what is F? F will be a function on G, which is smooth, with compact support. So the support will be in a small open compact subgroup, which is imaged by the exponential map of a lattice. In the Lie algebra. And you look at its trace. So it is in some sense, if you look at the representation of the unity, the identity, because the functions here are restricted to small neighborhood of 1. And this is the sum with complex coefficients on the nilpotent orbital, on the nilpotent orbit in the Lie algebra of G of this nilpotent orbital integral. This is an integral on the nilpotent orbit. You're in the Lie algebra, donc you are going to take f x. This is a function which is supported here. And you take its Fourier transform. Fourier transform. And so you have to measure some character. There are a lot of things to choose to do that. And you integrate on an invariant measure. You have to prove that losses converges and things like that. And this is a formula with C pi of O, complex numbers that are unique. And the homogeneity is that if you look at so I could for a function phi we support on the Lie algebra a complex support. And if you write phi t of x is equal to phi, or you don't see that, t minus x, then you have mu 0 phi t is equal to t the dimension of the nilpotent orbit over f divided by 2 is always an integer, is an even number, the dimension divided by 2, mu of phi. So these two things are the size. These two things imply the answer to the general question is yes with the polynomial with coefficients that are with some polynomial like that, and necessarily the coefficients are rational number. And the coefficient will depend on this element. And this pi of O, they are not very well defined because they appear, but they have made a lot of choices and normalizations. And as you know, normalization is always a problem in this field. So what I claim is that, my question before is equivalence is false when I say it is equivalent, but it's almost equivalent to the following question. Can you find a normalization so that these constants associated to pi are all integers? It is not known they are rational numbers. So there are other things. We know these constants are very important and nobody knows anything about them except the one associated to the orbit 0 and the one associated to the orbit so that the bigger one, the maximal orbit, I will tell you that. Now, when O is a trivial orbit, it is known that C pi is the formal degree. pi when pi is tempered. This means that it is not zero if it's for me up to a sign. So if pi is supercuspidal, it's not be zero. If pi is square integrable, it's not be zero. Otherwise, it will be zero. Because the formal degree, when it is tempered and not essentially square integrable, it is zero. So it can be zero. So, and now look at the set. Look at the set of nilpotent orbit such that C pi of O is different from zero. The nilpotent orbit, there is an order. O is smaller than O prime if it is contained in the closure. Give you an order. If you take an element that is maximal here, in the set, for a maximal nilpotent orbit in the set of orbits so that the quotient C pi of O is not zero, then Meglin et a+bpjéh you see, it is not very recent. Gave a formula for this value. It is, well, they have to choose normalization so that it will be true. It will be the number of degenerate Whittaker model associated to O. So I will not explain to you what it is. The formula looks like that. Is the dimension over C of the maximal quotient of V, on which, I will tell you, to O, you associate a smooth character of the unipotent radical of a Borel, a minimal parabolic, and V theta is a maximal quotient of V, the space of pi, on which the unipotent radical U acts by theta. It's very interesting. So for instance, if O is a regular orbit, then and if say pi of O is different from zero, it's equivalent to say that pi is generic. When theta is not degenerate, this corresponds to the maximal orbit, the Richardson orbit of the minimal parabolic. And the other coefficients are totally unknown. Nobody knows anything about them. For GL3, Fiona Murnaghan, if you look at, then you have three orbits, nilpotent orbit, zero, the regular one, and another one. And Fiona Murnaghan in the 1990s computed explicitly for supercuspidal representation this constant with some normalization, of course, but we don't know what it means. I don't know. It should be a big mystery. So I have to do, this is where I see. So the theorem, Guy Henniart and me, is that for GL and D, you can prove that the constants are integers and everything goes. But before telling you the result in general, I think for people who are not used to, even for me it's very useful, I will tell you what is the result for GL2D. And the result for GL and D is just the same. It will probably be better to understand first. So, for GL2. So I will explain GL2D, then I give you the general result for GL and D, and then I will tell you a question about the case where it is the field of characteristic P, where I know nothing in some sense. Well, GL2D. So Morra. So you start with lattices. So D over F is the central division algebra. Of dimension D square. When D is equal to F, D is equal to 1. You have OD integers, PD uniformizer. Okay. And PD is the maximal ideal. And QD, the order of the residue field. So now the Morra lattices. So you have M2 of OD. So which contain, and now you put OD, PD, OD, PD. No, OD. And you go on. You guess what it is. And you go on. PD. You multiply everything by PD. And so on. And then multiply. And so on. Now you take the groups. So this is GL2 OD. This group of units of this one, which is Iwari. Group of, and here it is the pro-P Iwari, 1 plus P, and this one, D, which is 1 over half. And this one will be 1, I call it 1. And so on. I1, which is 1 plus PD, this one. So this one is not a pro-P group. This one is not a pro-P group, but starting from this one, you have pro-P groups. So this one, this one, this one, and then you have the congruent subgroup of these groups. Not the congruent subgroup, I mean, you have 1, 1, 2 plus G, which is 1 plus PD. This one, how can I call it? I call it I 1 over 2. Something K 1 plus V, which is 1 plus PD G plus 1 and contain I 1 plus G, and there is what it is. So you have the Moy-Prasad subgroup and the other. What do I want to do now? So take B, which is the Borel, the upper triangular subgroup, and you compute B, G, and one of this group. So I will call H0 is equal to K1, I1, excuse me, I1 over T. Okay, and HG I. And you compute this to 0, and you get, I don't remember, so one is QD, the other one is 2QD, but the first one is 2. Maybe the opposite, I don't know. No, it is like that. And you compute, and you get that. And now that I know about things about my groups, I look at representation. You take a field that is any field, and you look at the parabolic induction. So you take sigma, which is let us take irreducible, admissible representation of the triangular group, no, the diagonal group. Which is isomorphic to B star or B star. And you induced, and you have the following thing. This is equal to 1. No. On K, open compact group, small. If you see, the idea is that you look at a representation, you restrict it in the neighborhood of identity. So this representation restricted to the neighborhood of identity is just this. So now if you want to look at it doesn't matter if the field is complex number or anything. Then you take the vector invariant by HG when G is bigger than something. Then what it will be? It will be, if you look at this dimension, it will be dimension R of sigma by G by B. And it is dimension R of sigma simple. Kind of. Okay. So now it's but it is as a function on as I take a prop P or something. I will enter it. So the idea is that if you have any reducible admissible representation, we restrict it to a neighborhood of entity, it will be simple. And here, simple is that is 1 and be of G of 1. So now think of the Sternberg representation. It becomes tricky, the Sternberg representation, if characteristic of the field is P. How it is defined? You have this exact sequence. Exact. So of course, the dimension Sternberg representation upon fixed by AG should be the dimension of this minus 1. Well, this is clear when the field is not of characteristic 0, or characteristic P. But what you have to prove is not that easy. So AG exact. So Morra proved it. And we have another proof for F is equal to QP. D is equal to QP, P different from 2. And we have a proof with Henniart in general. In fact, of course, there is if I was thinking of GL&D, the analogous results, we don't know how to prove it yet. On the characteristic is P. But for GL2D, we have a proof. And then you get your result that the dimension of R of ST is equal to 1 minus 1 plus so now supercuspidal. So of course, at this point, I have to suppose that the characteristic of R is not P. Otherwise, I get into trouble. So when characteristic of R is P, this is more. But to see characteristic. Then you prove that dimension is equal to I, which depend of H, plus B pi. With integers. And we know what are these integers. The first one, we know it because of the Jacquet angles. By the Badel, so everything you are characteristic from P, this group are pro-P group, everything is semi-simple and things like that. All these things, I write this for irreducible representation. That is the same thing for finite length representation. And this goes to the Grothendieck group. You can also define the Grothendieck group of finite length are representation of GL₂. So this can be defined by like this by linearity. So suppose that R, to simplify, is algebraically closed. Then you have the Badulescu-Jacquet-Langlands morphism. Jacquet-Langlands. when R is equal to C, and that goes from Grothendieck GL₂ D, Grothendieck C de D star 2T. This is a central divisional algebra over F of dimension 2D to the square. It is written usually LG to recognize it from the direction. Then we prove that I, and it is surjective. And we prove that, excuse me, I wanted to put this. This is, well. I want to write a₂, b₂, doesn't depend on H0. The dependence of H is only here. Here, these are integers depending only on pi. So we have a₂ is equal to minus dimension over C of. So this is a virtual representation. You can define the dimension of a virtual representation by linearity. The virtual representation can be not zero, and the dimension can be zero because defined by linearity. So I did that for C, but you can also replace by a phi of characteristic. This can be generalized by Mingus. You can take arbitraries. So no something. So suppose also, and now what is for this? Well, this I already tell you what it was. So b₂ will be the dimension of v theta. Here you suppose pi irreducible, where theta is not degenerate, is not trivial, or character. Smooth. All character of U, the upper, strictly upper triangular. That's it. So for GL₂, for function of rank 1, we are quite happy because there are only 2 nilpotent orbits, for instance, 0 and the regular one, and then you have some interpretation. Now I'll give you the finite, what we prove for GL₂. It is the same thing. Here, b₂ is equal to 1, is equivalent to b₂ different from 0, equivalent is always equal to 1 if d is equal to f, because unicity of Whittaker model or GL₂F. But when d is different from f, we can have b₂ bigger than 1. And in fact, b₂ is never 0, because I suppose my representation to be super cuspidal. But in fact, this is, I should not have been put supracuspidal. I should have put pi in general. B-pi is never zero because you suppose the representation to be infinite dimensional. If it was finite dimensional, B-pi would be zero. And B-pi must be not zero. So the dimension goes to infinity. So now the only restriction in GL, G is equal to GL and D. So theorem with Henniart. So I'll start with pi irreducible, R smooth, and the characteristic of R. Different properties. R representation. So it is automatically admissible. It's always admissible. Then there exist integers. C pi lambda for the partition lambda of n, such that on some open compact subgroup, pi is equal to the sum of sigma where P lambda is a upper triangular group by block with maybe see if lambda is equal to. So round one, every representation look like that, linear combination of that, this virtual representation. So now, what is so you deduce a formula for this polynomial that we wanted, deduce from that. And if R, suppose R algorithmic law, and if you have, and you look at the Jacques-Langland's bodiless coup Jacques-Langland's from the Grothendieck group over R, GL, DN, DF, R, GL, and D. This, and this is compatible, this is compatible with Jacques-Langland's. Here, a partition of n give you a partition of Dn, but just by multiplication by D. So you have that, so this function z pi of lambda extend to the Groton group, and you have that c d lambda of pi, or pi in the Groton group of GL₂ is equal to c lambda or LG for all lambda. Okay. In general. So these constants are compatible with Jacques-Lagrange, the best sense. So in something with the question that I raised at the beginning, the general question, if you work with mod P representation, we can wonder if the constant in the Stefano-Morra formula is related to the Scholz correspondent for mod P Jacques-Lagrange. I don't know. And if you want to look also at the, this is for lambda. The explanation here is that the partition of n parameterize the independent orbit of M and D. You have lambda is not nilpotent orbit. The dimension of O lambda is equal to 2 d square, I think, d lambda, where d lambda is equal to sum from lambda E, lambda G. And when you compute P lambda G et G, you prove que this is equal to, I need to look at my notes, is P lambda P D lambda D. Here. So you will know in the and you have also a formula for give you the coefficient maximal where C lambda is not 0, exactly like the dimension of some covariant. And what time is it? I hesitate with what I am going to tell you. Maybe I will tell you something else, which is before I will just write. So so the formula to remember is this: P H equal to sigma sub lambda, Cp of lambda, B lambda. So this is very neat, it's a nice formula. And I go back, and now I go back to Morra. I go back to P different from 2, GL₂QP, car finite, R finite, characteristic equal to P, and I take the pro-P work. So the formula of Morra, if I am not mistaken, is that from that pi when Hg, when pi is super singular, irréducible, absolument, is equal to -2 plus k. I'm right? Oh, I didn't put it in my, it is not here. I think it is this. And I discussed with Yong-Kon Wu, who told me that this polynomial, I hope this, yeah, I think it is this. It is an Hilbert polynomial. Of the graduate, the space is V, huh? Of the graduate of the dual of V, well, seen as a module over the grid which is isomorphic to polynomials. So all what I told you were the complex number or particularly from P, the degree of the polynomial is the Gelfand-Kirillov dimension, which had been defined for representation mod P. When you look at representation mod P, you have this, you restrict them to uniform group, uniform subgroup, and you can define the Gelfand-Kirillov dimension by doing this restriction. The more important group, all of them are uniform. I can prove that. And mod P, I see no other polynomial than the polynomial, the Hilbert polynomial associated to the graded dual. For GL₂QP, it seems, I am not sure that it understood well. It seems that the polynomials that appear are this exactly the Hilbert polynomial. One should not expect this to be true in general for any V star is a pair H module which is finitely generated, but it is special because this is a representation of G GL₂ that has been restricted to a _p worry. It's not any representation of the admissible of a _p worry. Well, the question I can raise, it would be interesting to understand better the Hilbert polynomial of the representation in the category C that had been introduced by Schran, and who is here, and Morra, who is here, and Prey, who is not here, and Yokan, who is not here, and Narcish. So this is the end of my talk.